Okay, good afternoon, everybody. Welcome. Before we begin our seminar, I'd like to acknowledge the traditional custodians on the land that we gather, the Jabberkai, Irriganji and Guma Yudinji peoples. I recognise their continued connection to land and that they have not ceded sovereignty, and I pay my respects to elders past, present and emerging. And so I'm very pleased to welcome Kim today to speak with us about his work on terrestrial LiDAR scanning and vegetation structure. So first I'd like to just introduce Kim to you. So Kim is Associate Research Professor at GHENT University. He did his Bachelor of Science and Masters of Science in Bioscience Engineering at Catholic University in Leven, and a Masters of Science in Remote Sensing from the University College London, and a PhD in LiDAR remote sensing from Wageningen University. He's since completed 2 postdocs at the University College London and Ghent University. I'm very excited about the possibilities of using terrestrial LiDAR scanning. I think it has enormous potential for improving our understanding of forest ecology and ecosystem science. And so I'm very excited today that Kim has agreed to give us this presentation. So welcome, Kim, and thank you for coming.
Thank you. Thanks for having me. So yes, my name is Kim Calders. I'm based at Ghent University, and I'm part of a lab called CAVElab. So we are a group of about 20 people, 2 professors in there. And we're not doing only LiDAR, we're also doing vegetation modeling, traditional forest sensors, and we mostly work in tropical forests, but we also, especially since COVID, we have a focus on temperate forests as well. So today I want to talk a bit about why terrestrial laser scanning, or TLS, can be a useful tool for vegetation monitoring. And then I want to move on a bit to fusion and the new advances that we're seeing in the field, like automated laser scanning, and how that sort of embeds into a new global network of automated laser scanning that we're trying to set up. So my interest for using LiDAR came more than a decade ago. I've always been quite an outdoorsy person, and so on the left you see the 3 pictures. These are just 3 forests in Europe, and you can see that they're visually very structurally different. And on the right you can actually see a photo of this Robson Creek, so very close to where we are now. And even though they're all called forests or woody vegetation, the structure of these forests can be quite different. And even in just one forest, the structure can vary even through time. So this is here you can see a cross section, a transect of a deciduous forest near Ghent, actually, where we are collecting structural data every month. So this is actually from this year. This is work that Louise is doing, and we are scanning this transect every month. And of course, in the winter, so at the start of the year here, there are no leaves on the trees, and you can really see that leaves emerging on the trees are structurally changing how these forests appear. So it's not only that forests are different, even one specific site, one forest, is also structurally very dynamic through the season. And of course, what we're also seeing is an increased number of disturbances, also in Europe. But here I have an example of Litchfield National Park in the Northern Territories, where you can see that a fire went through in September 2019. Of course, obviously visually very much changing the structure of this forest. But what I found even more striking is that just a few months after that, the site is clearly recovering, leaves are emerging again. And of course, this is having a structural impact. Because what is structure for us? Structure is the spatial arrangements of all the elements that actually build up a forest, or leaves, twigs, stems. So forests are very dynamic by nature, but also with the impact of disturbances, either natural or an increased number of disturbances that we're currently seeing in many parts of the world because of climate warming. So as I said, how we try to monitor these forest dynamics is by looking at structure. And ecosystem structure is quite an important one also for biodiversity, and it's also one of the essential biodiversity variables, EBVs. And if you want to monitor the structure, well, we need some understanding of structure at a given moment in time. And so I call this the baseline structure of forest. And traditionally, well, there are two good ways to do it, or good ways, there are at least two ways to do it traditionally. So you can either go in and you can take measurements, either if they're destructive or non-destructive, or we like to look at forests using satellite data. And if you combine them both, you can make maps. And people have always liked to map stuff. I like this. I like this map a lot, especially when I give a presentation in Australia. So this is the sheep and wheat map in Australia. So people always had a very keen interest in making maps of where items, or here sheep, are located in space. But if we bring this back to vegetation, I want to show you this example. Some of you might be familiar with this. So what you can see here is on the first row and the second row, they are two pantropical biomass maps. The first one by Sacchi and the second one by Baccini. And both of these maps have been made with the same satellite data, but they've been using different in situ data and different modeling behind linking the in situ data with the satellite data. And they came up with two different maps. And in the bottom row, you can actually see, based on a study by Ed Mitchard, the difference of these two maps. And you can see that even though if we use the same spaceborne information and we use in situ data, you can come up with very different products. So this clearly is, this is a good illustration why maps don't always agree. And it even hints more that measuring forest structure is very, very complicated. And on top of that, if we want to monitor forest structure, we don't only need to measure forest structure in one point in time. We really want to continue this. So we need repeat measurements. And if you really want to detect change, so if we want to monitor, we need some tool that is objective. So for example, there's these really great classifications in Australia from SPECT, and they look very visually very appealing and they look realistic, but we can question, like, how quantitative is this? Is this good enough if we want to monitor forest structure through time? I also put this one here. This is actually a little side project that Matt Disney from UCL did, where he asked in his daughter's class for everybody to draw a tree. And people just have a very different vision or an idea of how a tree structure looks like. So it's very important that we can use tools in vegetation monitoring that give us objective measurements of how the tree structure looks like if we want to implement if we want to implement forest monitoring. So what we are using is laser scanning or LiDAR. LiDAR stands for light detection and ranging. And the nice thing about this is that it's actually a relatively direct measurement of location. So what it's basically doing is, so here you have this terrestrial LiDAR on a tripod, and you have the tree, and what it does, it fires out a photon. This photon will hit some kind of element in the forest, and it will return the energy. And basically, by measuring the time that it took from this photon to go to the tree and back, and because you know the speed of light, you can determine the distance. And these kind of instruments, they measure with 100,000, 300,000, 1 million measurements per second, and they build up a complete 3D image of points of the forest. So how does this look? So here, I mean, of course, it's always very difficult to show you some of the data on a 2D screen when you're talking about 3D data. But what you see here is a LiDAR image where you have the azimuth and the zenith. So basically the two angles for firing these photons. And then the coloring is by range. So the distance from the instrument. And you can really see this is actually, this is in Robson Creek. And you can really see that the forest structure is quantified quite nicely here. Here's another example, and it should be coming through fine. So here you can actually have here's a 3D animation of a point cloud. So similar as the slide before, but here you can really see the 3 dimensions. So this is a point cloud of a forest in the UK. The coloring on top is actually, we're not only measuring X, Y, Z locations, and there's also often a camera integrated on these instruments, and this is giving this coloring. But important to notice here, this is not a model. This is just X, Y, Z points of the forest structure. This is in Whiteham Woods, where we also have the canopy walkway, and you can see that we get quite a nice representation of the forest structure all the way to the top of the canopy. So TLS actually has quite some history in Australia. Up to 20 years ago, the commercial instruments, they were really not very suited for working in forests. And people at CSIRO, they built essentially the first TLS instrument that was really purposely built for vegetation monitoring. So it was called the Echidna. So it's the yellow box or the orange box that you can see there. And this is Glenn Noonan operating this instrument. It was a very nice instrument, but as you can see, it's not very practical. You need to bring in a lot of equipment just to do a few scans in the forest. We've quite advanced from this, and now most of us, we're all using these commercial instruments. So there's a whole range of them. There are not that many manufacturers, but there's definitely some options to choose from, going from the lower end, also the cheaper instruments that you can see in the bottom right, to really the top of the line, like the one you can see in the middle here, this Regal instrument. And with these kind of instruments, it's really a matter of what kind of data quality you're after. Is often also quite linked to the price that you will pay for this instrument. It's quite important to notice that these manufacturers are generally not building these instruments for us. We're not a big market for them. It's a lot of mining companies, police, engineering, architecture. This is sort of the main market for these people. But since like 10, 15 years, the instruments that are being provided for the market, they're quite well suited for vegetation monitoring. I'm not going to go too much into detail of how we collect the data, how the scanner works, how we analyze it. I want to more focus on the applications, but I quickly want to highlight there's basically 2 ways to work with LiDAR data. And on the right, you have the detailed assessment. And that's actually that's the kind of the data that, or the way that most people deal with these LiDAR data. So you go to the forest, you put your instrument in multiple locations to reduce the occlusion. And you typically build up like these 3D images, like you see in the circle below. So you really make a 3D scene, a 3D point cloud. Typical applications are like, for example, biomass assessments. But also what you can do is just take a single scan or a number of single scans, which you treat as independent units in your sample. And you analyze them using gap fraction approaches, and I will come back to this later, because the advantage of this is it's very fast and it's also more robust and automated. So there's also some applications that are definitely well suited for a single scan approach. But first, I want to show you a few examples of the detailed assessment. So typically what we do when we do this detailed assessment, so we do this multi-scan. So here you're looking at a forest from above, and this red laser beam is scanning the forest, and it's creating this kind of point cloud, what you see here. Of course, this is an animation, and the data in real life looks a bit more complex, but this is just to illustrate the process. So once we have the full point cloud, the next step is to separate this into individual point clouds. So we do the segmentation of the point cloud. And then the next step is basically to convert this 3 point cloud into a tree model. So we're going to enclose this points with a model, which we call a QSM, or a quantitative structure model. So we can actually start calculating some elements of the tree, like, for example, volume is the obvious one, because there's been a strong focus on biomass, but also branching architecture, topology. It's now possible because we have this structural model. So when we first started doing this work, almost more than a decade ago, the first question that we wanted to answer is like, well, how good are these point clouds and how good are these QSMs? okay, it's nice to have this new fancy tool, but if we can't validate what we're measuring, it's not of much use, and it will be hard to convince people that there is actually a lot of potential in these new technologies. So this is work that I did in my PhD, and this is in Victoria, and this is Rushworth Forest, where we're lucky enough that people are actually doing a lot of harvesting to establish new volumetric models. So we were able to scan about 70 trees before they harvested them, and they were weighed on site. And so on the crane, you can see that there's a scale hanging there, so we could measure the fresh weight in different classes as well. So the smaller part was put in the shredder and was weighed that way. And then, of course, also a whole selection of discs was collected to bring back to the lab, so we could calculate the fresh to dry weight and the wood density as well for those specific trees. So what did we learn from those measurements? So here, what you see on the x-axis is the field measured dBH, so the typical diameter measurement with a diameter tape. And we see the LiDAR measurements on the y-axis, and you can see very good agreement, an RMSE of only 2 centimeters, and quite a good match. And this is what we sort of expect. Of course, we can measure dBH quite well on a lot of trees just in the field, so no surprises there. But it gets quite interesting when we look at height. So here we have reference tree height on the x-axis. So that's actually the reference height is the height measured when the tree was harvested, and we put a measurement tape on the ground next to it. And then in the red, you have the traditional height measurements. So you can see it's quite a good agreement until like 16, 17 centimeters. And then it started to deviate a little bit from this. But with the LiDAR, we actually see quite a nice match, sticking quite closely to the 1-to-1 line, which is a dashed line. So we definitely see also on the right that the residuals for measuring tree height with LiDAR are way smaller and more centered around the 0 residual than when we do this traditionally into the field. And these were not very complicated trees. This is not a tropical forest. But what we're really interested in was like how good are these QSMs? And so typically when we have this volumetric QSM, we use wood density or basic density to convert it to a biomass, above ground biomass. And for this specific case in Rushworth, you can see here on the left panel, you have on both panels, you actually have the reference biomass. And so from the destructive measurements on the x-axis. And on the left panel, you have the typical allometric model estimate for those trees. And you can see that there is, after 1 ton, there is a consistent underestimation of the biomass. Whereas if we look on the right panel, so this is the TLS, so on the y-axis, we have the estimates of above ground biomass using LiDAR, that we have a much better agreement with the destructive measurements than we see with the allometry. And if you look at this at the plot level, for this specific case, we could conclude that allometry would underestimate the biomass with 30%, and TLS was leading to approximately, it was a 9 or 10% overestimation. This work has been done also like more than a decade ago, and part of the overestimation in the TLS was also clearly from the presence of leaves. Back in the day, we didn't have really any tools to remove leaves from trees. So I think if we would reprocess that site, probably that 10% would go down a few percent as well. But I think it's quite important to realize that after a certain point, so the 1 ton here, the allometric models starts to deviate. And this is typically related to that allometric models are generally built based on a calibration data set to build a model. And often in these models, there is data from smaller trees because they're easier to harvest, and only fewer large trees. So it makes sense that if you build a model that way, that if you're going to plug in large trees, that they will perform less good than if you put in smaller trees, which are actually quite well represented in the calibration data. Whereas with TLS, you don't have that. You are assessing the tree as it is. You're collecting the data from the specific tree and you're modeling it individually. So that's clearly explaining some of the difference that you're seeing here. After this work, we have continued doing this. So the work that you saw before is this Calders 2015 data set you see in Australia. But we've been doing this in many places in the world with other colleagues, also in tropical forests. And here you can sort of see on the right, this is a summary where we have the harvested or the reference biomass on the x-axis, and then estimates of TLS using the same approach as I explained before. And you can see that if you look at the top panel, so this is the full range of biomass, is that we have generally a very nice agreement between estimating biomass from TLS, even of trees up to 40, 50 tons, so very, very large tropical trees, compared to destructive measurements. If you zoom in a little bit to the lower panel, so this is actually a snapshot of the full overview. So these are just the trees to 1 ton. You can see there is of course a little bit of spread around the estimates, and we know that for smaller trees, often these QSMs approaches, TLS approach, perform relatively less good compared to large trees, and that's often related to the ratio of leaves versus woody material. And smaller trees tend to have proportionally more leaves, which are causing sometimes a bit more problems in our analysis. But I will come back to this later. And this is another case study, a case study that we published end of last year. This is work that I did in my postdoc when I was in the UK, and this postdoc was not related to biomass at all. We were building a digital twin, which I will come back to later as well. So this is the Whiteton Woods. This is a forest owned by Oxford. It's a very well studied. They claim it's the most studied woodland in the world. So many people are working there for a long time. And we scanned, quite a large area there, but we did the analysis on a 1.4 hectare area where we basically extracted every single tree. So this is an overview of all the trees in here. So it's about 800 trees. And you can really see that, so they're colored by species here. Even one species can take on quite different shapes in this forest. And when we were doing this assessment of biomass, just to check, well, we are in the UK, and we always assume that we know very well how we can measure our biomass and our carbon in European forests. We were quite shocked to see that these measurements were quite off. So what you see here is on the x-axis is the allometric model estimates that you would typically get if you would use the typical approach, and on the y-axis you have the TLS estimates. On the right panel, you sort of have a zoomed section of the smaller trees, and you can see overall that we predicted a lot more carbon in those trees. Overall, a factor of 1.7, so 170% of what would be estimated using these allometric models that are used to do the reporting to FAO. So we were quite shocked by this, especially you can see this one tree E here, and that is really off. The big trees are quite poorly estimated, and this links back to what I said before, that large trees often don't do well in these allometric models. What we did is, well, we were like, well, first thought that came to our mind was, well, we must have made a mistake here. It happens, you know, you have diameter, you have circumference, you have centimeters, you have inches. So we looked and looked and looked, and we couldn't find much. So we did contact the person who made this allometric model in the 60s. So this is also an old model. This is the photo on the left there. So complete on the left, this is Bob Bunce. This is the person who made this allometric model, and we tracked him down, and he was living in the Lake District, and we went back with him to some of the sites that were included in his analysis for making these models. And one of the things that I still remember that he said to us is like, oh, you're one of the first persons ever to contact me about this paper that I once did, because he did it as one of his early research projects when he was in his 20s, and then he went off to do some other work. So it's quite striking that a model that is so well used actually is not linked back to the people who really developed it well. So we were thinking back about it, and having learned a lot from this, was quite a nice experience, and it really illustrates that we need to be careful when we apply these allometric models. If you find something in literature look where the data is coming from, what is in the calibration data, because these models for the UK, they're actually built with a lot of data from the Lake District. The Lake District is not really a representative area for lots of the areas in the UK, so it's not so surprising. Plus, forest management has changed a lot. When the models were made, there was still a lot of coppicing going on, and now coppicing has been abandoned, so woodlands are developing quite differently. So this was a nice example, actually, how we could demonstrate with TLS that we should be careful with using older models, and we should probably revisit some of the models that we're currently using. One cool thing, I'll briefly mention it, that when we did this full analysis, so we did all the trees in the forest of this 1.4 hectare up to the centimeter diameter, is that actually if you want to represent, well, if you would want to estimate 50% of the total biomass of the site, we would only need the 39 largest trees. And so out of these 600 trees per hectare, you would only, if you would only estimate the 39 largest trees, you would get 50% of the biomass. If you extrapolate that, 90% of the biomass is in the 200 largest trees of these 600. So in 1/3 of the trees, and the lower diameter of that would be 24 centimeters. So there's a lot of biomass in the large trees. So it's even more problematic if we can't estimate the biomass of these larger trees. I don't want you to go home and think that TLS is a magic tool, because it obviously isn't, and it's often perceived like this. It's like, wow, but I think we should also be critical of what it can and what it can't do. Some of these issues, or potential issues, are related to simple questions like, what is a diameter? So of course, we put our instrument in many locations in the site, but sometimes there is occlusion, and that's something that we can't deal with very well. Apart from doing more scans, there can be buttress roots as well. So how are we really modeling this? We're often using a cylindrical approach. We can use meshes. So there is definitely room for improvement and addressing these issues, but it's important to know this. And probably the most important one is biomass. We are not measuring biomass with terrestrial laser scanning or any laser scanning at all. We are just measuring an approximation of volume, and then we apply wood density. But we don't do measurements of wood density. We use what's in literature. And this is a great example. There's a tree in Whiteland Woods. And if you would look at this from a distance, it looked healthy. There's leaves on there. But if you go very close, it's completely hollow inside. So quite important to keep in mind, we're not measuring biomass, we're not measuring carbon, we are just measuring volume, and then we're calculating or deriving these other parameters from it by multiplication of other parameters. So moving away from the biomass is what we're working on quite a bit now. Is called this digital twin. Of course, it's a buzzword, but how we see digital twins is a structural input for other models. And we are using quite a lot these radial transfer models. So what we're trying to do is we have a real forest, and we want to build it completely in 3D. So not just structure, but also, for example, the spectral information. So we can use that model to simulate any sensor. We want to use this kind of approach to benchmark the sensors that we have in the field, but also if you would have 10 PAR sensors in the field and you can really validate that what they are measuring is sort of what they should be measuring, so you can look at the radiation regime, you could potentially put in 100,000 virtual PAR sensors, and you could measure PAR in places in your forest that are maybe very hard to reach. You could also put it as a function of the canopy height. So this is kind of the approach that we're taking with this digital twin here. So when we want to make these digital twins, again, you have the QSMs here, which you see in brown, but we need to add on the leaves, and we need to allocate we need to allocate spectral information if we want to use this, for example, with rate transfer modeling. So here, again, you have the complete stand in Whiteland Woods, which we also put leaves on. We put the spectral information in there, and these are some examples here of what you can actually do with them. So we have Whiteland Woods that exist in real life. So we took, for example, here you can see on the right a real hemispherical in the real Whiteland Woods, and then on the left you have a simulated hemispherical photo in the virtual Whiteland Woods at the same location that we took the photo in the real forest. And if you just visually look at it, they're very looking alike. And if you look at this quantitatively, I think they agreed, the gap fraction agreed within 1%. So we're quite happy with this approach. It has a lot of potential. We're obviously currently further developing this as well. But this is a great kind of approach, or like newer use of current use of using terrestrial laser scanning in research. It's not limited only to ground-based sensors. So this is an example of a Sentinel-2 or a drone image. So once you have this virtual forest, you can basically simulate any sensor that you want. You can even develop your own sensor. If you want to develop your own satellite, you could simulate, you can parameter that, you can put some parameters in there, and you can calculate how the data would look like above this specific forest. Two limitations that I wanted to highlight. So TLS is not magic. Also dealing with leaves. So a lot of the work that you saw here has been done in White Woods, and one of the great advantage is, so I still use White Woods, is really my calibration site for a lot of our algorithm development as well, because we have leaf off and leaf on data. So when we model the structure, we obviously want leaf off point clouds. And here we can see an example of a tree. I think this is Guyana or French Guiana. So this is a tropical tree. It's around 40 or 50 meters tall. And at the moment, like there's been a whole range of new algorithms being developed now to remove leaves. So we can remove leaves. There's a lot of progress there as well. But of course, it will come at a cost because leaves increase the occlusion in your point clouds. So we really need to focus on dealing with this as well in the future. And then important is also good to know that TLS is very limited in space. So typically the sites that we do, they are 1 hectare. That's a typical gem plot size. So if you want to do some upscaling, what we've been doing is linking this as a data fusion, where we link TLS, which you can see on the left, with drone data. So this is actually Robson Creek again, where we did some work in 2018. We also went to GRO, and we went to Oliver Creek and some sites in Northern Territory, where we collected drone LiDAR, which you can see in the right here, and you can see TLS data. So you have Oliver Creek and Robson Creek here. And you can see in the lower row, when we fuse these data sets, you overcome some of the occlusion that you typically have with TLS on the top, in the tropics, and some of the occlusion you have with drone LiDAR at the bottom. So you come to this more complete image. And if you zoom into a tree, so if you look on the panel B and C, you can really see that we're overcoming some of these occlusions, especially in the upper branches in those trees. So there's a lot of potential for this fusion. Have to mention here, this is a very high-end drone. This is like when we do fusion, and this is still something we're learning, is a drone data set, even though there's a point cloud, and a TLS data set, which is another point cloud, we need to be carefully to just fuse them, because they will have different uncertainties, they will have different laser optics. So we need to really understand what we are actually fusing together. This is just an illustration here, a summary of different sensors, like LiDAR sensors on different platforms. I've talked a lot about TLS, which you can see in the right here. But you can put this sensor on the drone, as I illustrated in the slides before, and then very typically it's also the ALS, so the airborne LiDAR. And typically there's a scale difference. So you could use an airborne LiDAR sensor on a helicopter or an airplane. You can cover a much larger area, whereas TLS is mostly restricted to smaller areas, but it gives you the most detailed data, which you can really use to do fundamental research or to calibrate models, build new models. So that was a bit the section about the detailed assessment. I want to now talk a little bit about this rapid assessment that I talked about. So with this rapid assessment, we just take a single scan in a location and we analyze the gap fraction using methods that were developed by David Jupp from the 2009 paper, but I'll illustrate this in the next couple of slides. So this work started in 2014, where I did some scans at 48 measurements day in the forest in the Netherlands, at 4 locations, just a single scan. So we started in February in leaf-off conditions, and then of course through the growing season. So leaves are coming out, they're emerging, and sort of by July, you have a full leaf onset. You can see the different point clouds here. Well, they are point clouds, but they are just single scans. So I projected them here in polar coordinates. So you can see they're colored here by apparent reflectance. You can really see that the leaves are emerging throughout the season. So if we analyze that, we typically get these profiles, these vertical profiles, where you have PAVD, so plant area volume density. So you can think about this as how much plant stuff there is as a function of canopy height. And what you see here is that, of course, in the upper canopy, this peak increases throughout the season, but we also see different changes in different layers of the canopy. So if you take the integral under this vertical profile, you basically get the PAI, what you're probably more familiar with. If for all these 48 days, we would plot this, you typically get, so you have the day of year here on the x-axis. So you start in leaf of conditions, so your PAI is very stable. Then suddenly you have this very steep increase in PAI, and then it flattens out again. So you get this typical phenology curve for leaf onset in the forest that we have here. One of the cool things that came out of this as well is that you can, in the gray band, you can see this little dip there, which happens in all the locations. And this was actually the effect of a storm, not a big storm, but when I did the measurements the day after, I could really see some twigs lying on the ground. And if you, I evidenced this then with some data from the weather station, which was the most windy day of the year. And this is really was convincing evidence for me that through this approach, through this kind of monitoring approach, with gap fraction analysis, we can really detect small changes in the forest structure. Just to mention here again, even though I showed one profile, because you're dealing with these 3D data, you can easily analyze this as a function of canopy height, different layers in the canopy, upper layer, lower layer, mid layer, it's all possible. I left Wageningen after this 2014, but people have continued measuring this. Even at some point, we continued also into the autumn season. But one of the things that you can really see from this time series of 5 years is that there are data gaps, and that's often linked to, well, we don't always have an instrument available. Projects need to be carried out in different countries. So TLS has a lot of potential, but it's really not the tool to do this. And this is also illustrated with my wife here. So this is Easter Day in 2014, where, well, if you want to build this kind of data sets, you need to go and at some point, yeah, if it's a holiday, no one's around, someone will need to come. So I was finishing my PhD back then. So it's not very practical. You need to have people available. You need to have instruments available. So we were really thinking, well, this has a lot of potential, but this is not the way to do it. So we are exploring automated laser scanning. So what you see here is a leaf instrument. So it's a LiDAR that you leave on site. It can be run off the power if there's power on the site, or you can hook it up to a solar panel. And basically what it will do, it will take automated laser scans you can program it. You can do it once per day. You can do it twice per day. You can program it so it scans at night when there's less wind conditions. So it has a lot of potential. You see a lot of you see a few examples here. It's not just an idea that we have. We are actually equipping sites with these kind of sensors right now, and they have been built in Melbourne by Darius Kulvenor. It's quite nice little instruments. Here's an example of a data set, how it looks like. So this is in Litchfield National Park, where the scanner has been installed in July 2021 after fire, and you can see the recovery of the canopy in the profile on the right. So you have the PAI curve in the A panel, and in the B panel, you have these vertical profiles gridded throughout the season with daily measurements or near daily measurements. And you can really see that the PAVD is changing in different layers through time because we have these daily measurements now to keep monitoring these sites completely automated. So with this, we're trying to build this into a global network. So here's an overview of the sites that are currently are equipped or being equipped. So the green sites are equipped. So you can see a lot of sites in Australia. That's obviously because the instrument's been built in Australia. And all the orange ones are sites that have funding secured and will have sensors installed. And then there's one site in DR Congo where we have a flux tower that we're currently looking for funding. We are hoping that this map will grow very quickly. We only started with consolidating this idea of StructNet in June this year. We had a meeting in Potsdam, first user workshop, and we published this paper around how we see what our vision is with this network. So if you're interested in this, definitely email to me. A website will be coming soon as well, where we will provide more background and information about it as well. So to finish, I have a few slides on where I think or where we're going with this, and other people are going other directions. So one of the things that we're really focusing on is forest dynamics, and so linking back to my introduction, because we started doing a lot of this work around 2010. So we are sitting on data, some of the sites which have almost 15 years of data now. So here on the left, what you can see is actually data from UKFACE in New South Wales, where we have been doing measurements since 2012. And there you can really see the canopy changing. It's not just tree growing. Here you can also see that lianas are really changing the structure of these plots. So there's a lot of potential with these 3D data to look at forest changes, forest dynamics. So we're quite excited about this. We have quite a big project around this, which we call Space Twin, because we want to also not only observe these measurements from the ground, we want to link it back to how satellites are actually looking at these forest dynamics. Another quite new project that we're doing is looking at big trees. I've highlighted in my presentation why I think big trees are important. So this is a project that we're doing with the Natural History Museum in Belgium. So this is a tree in Peru. It's around 45 meters tall. There's a little person standing here, so it's gigantic. And what we are trying to do here is really, really quantify these structures of these unique large trees in the canopy. And how we do this is we want to have no occlusion in the trees. So we're not just scanning from the ground. We are very lucky through this project to work with this amazing team of professional climbers who take our instrument into the tree as well. So here you can see in the video how it's installed in a tree and how we actually move it in the canopy as well. This can only be done by this really experienced team of climbers that have been doing measurements. Some of them have been working with Halle since the 80s. So really exciting project where we're exploring scanning large trees, significant trees, but not only from the ground. We want to bring in the instrument. We're going to get a full understanding of their structure. And of course, other people are doing lots of other measurements about biodiversity. So it's a really exciting, cool project. And to finish off, I want to point to Nature is Data. So Nature is Data, you can go to the website, is an initiative of James and Gary, who reached out to me a couple of years ago. They've been using some of our LiDAR data and ecoacoustics to create this kind of representations, these art pieces with LiDAR data. So this ghost trees is actually using data from Rushworth, where it's built to make people aware of ecosystems that are under threat. So it had quite a lot of screenings, and until recently it was actually screening in the loom. So it was quite nice for people and for us to see that there's really a lot of interest in using these data because they're visually very appealing. And I think as scientists, we are definitely having some opportunities here to communicate this to the wider public. So thank you. That was it for me, and I'm happy to take questions if there are any.